Okay, hopefully you can hear me okay. Right, well, that's good to see young people getting involved in tech. Not quite sure how I can follow that, but there we go. So I'm going to talk about a project that I've been working on in the last couple of weeks, and this is communicating between a battery-powered Arduino and a Raspberry Pi. So why do we need to do this? After all, we could use ESP32s and Wi-Fi, and then all the security would be done for us. But Wi-Fi and ESP32s are power hungry and not really suitable for battery use. You could use LoRaWAN, but only if you have a gateway near you or are prepared to set one up. So some of the uses for battery powered devices, you can monitor things like temperature and light, or control things like doors and pumps. Some of these are obviously more sensitive than others, for example, opening garage doors, but even allowing hackers to manipulate seemingly unimportant messages can have bad consequences. So for instance, a hacker could say the temperature is different and thereby cause your control system to respond incorrectly. This is a couple of the popular devices that we could use. The NRF 24L01 board works at 2.4 gigahertz and does 32-byte packets at 1 or 2 megahertz up to 100 yards or so. The HC12 uses 433 or 868 megahertz serial comms up to 236 kilobaud, and this works up to about a mile. Both of these use about 10 milliamps when operating and have standby currents of a few microamps, but they're not secure. So if someone wanted to, they could listen in and even send their own messages. So before I talk about the encryption, I just want to talk about the hardware I used to test this. I'm going to connect an Arduino to a Raspberry Pi, and I decided to use HC12s. I'm measuring the temperature with a DS18B20, light level with a light dependent resistor, and supply voltage using a trick to measure the internal 1.1 volt reference. This is a Raspberry Pi 2 with an HC12 board connected. And I first had to do some modifications to the Arduino board. The board that I'm going to be using is an Arduino Pro Mini, which is this board here. And this board comes without the headers attached, but it also comes with a regulator and power LED, which is not suitable for battery use. So we're going to remove those. The first thing we're going to do is solder these headers on, and I found the easiest way to do this is to put these into a breadboard and then put the board on top of it, and then once that's in place, then we can solder a few of the pins in place, and then that'll make it easier to work with. So I just solder a few of the pins on like this. And once these pins are soldered in place, then we're ready to go on to the next stage, which is to remove the regulator. Now the easiest way to do this is to use a pair of tweezers and heat up either side of the regulator. You'll probably find it's easier if you put a blob of solder onto the regulator first. It takes a little while to do this, but with some perseverance then the regulator comes away like that. So we now need to do a similar thing with the resistor that connects to the power LED. So we put some solder on there, and if we heat that up, it should slide away from its pads, and then we can get the component away, as you can see there. So if I hold this up to a magnifying glass, you can see where the two components have been removed, the regulator on the left and the resistor on the right. So the next stage is to solder the remaining pins onto the header, because we only soldered a few of these pins on. And Having done that, we then put the remaining header on there, which is used for the serial communications. And then once we're done with the soldering of all the headers, then we're left with the board, which looks like that. And that's now ready to be used with the Arduino IDE. So this is the circuit diagram of the finished board. I put this all on a breadboard. The HC12 can be powered down by sending an AT command, but I tried this and it took ages to power down and still use 22 microamps. So I decided to add the P-channel MOSFET, which made it quicker to power down and also saved the 22 microamps. So this is the setup I've used to measure the voltage and current and make sure the board's working at the different voltages. So you can see on the left here I've got the power supply, and then next to this I'm measuring voltage, and then next to that I'm measuring the current that's being drawn. And on the oscilloscope, each of these pulses, which occur every 4 seconds, is going to this P-channel MOSFET here, which is connected to the HC12 board here. So the voltage is currently at 3.5 volts and it's happily working away. And if we now have a look at the Raspberry Pi, then you can see there's a program on here that I've written, which when I run that with the parameter decrypt, it's actually showing the message coming across the air, and you can see that it's showing the temperature 20.9, light level 957, voltage 404, which is 4.04 volts. And if I take the decrypt parameter off there, then it'll show the encrypted text coming across. So here you can see the voltage is set to 3.2 volts, and if we have a look at the Raspberry Pi, we can see that it's reporting 307, which is 3.07 volts. If we go back and adjust the voltage to 3.5 volts, like so, and then go back to the Raspberry Pi, then you can see that it's reporting a voltage of 337, so 3.37 volts. So it's slightly low, the voltage. Just finally adjust this to 3.7 volts, and again going on to the Raspberry Pi, it says 3.356, so 3.56 volts. Now if we switch the current, I'll just freeze that there, you can see that the current being used is 6.3 microamps. Now I said earlier that the voltage was being displayed low, so this is the code that's actually being used, and in the utils file there's a read VCC function, and if this is the value that is for a 1.1 volt reference. Now if I adjust that to compensate for what we've seen, so going from 112,640 to 117,400, then when we put that onto the board, and you can see we're set to 3.7 volts now, when we go across to the Raspberry Pi, you can see it now says 3.69 volts, which is almost spot on. So if we try this on different voltages, So 3.9 volts, let's get that on there, 3.9 volts. Then when we go back to the Raspberry Pi, it's reporting 3.9 volts. And then finally, if we have a look at 4 volts, this is reporting on the Raspberry Pi, this will be showing exactly 4 volts. So whether the meter is actually right or not, I don't know, but that's actually getting the same values coming back from the Raspberry Pi code as the readings as I'm getting here. The board seems to work from 3.2 volts up to 5 volts, which means it should be okay with a lithium-ion battery. And the sleep current is about 6 microamps, which would give decades of life on the battery. But I wanted to also measure the operational current, and for this I needed to use the oscilloscope. So I wanted to work out how much current the board was using when it was transmitting. So I put this 4.3 ohm resistor in series with the battery and connected the oscilloscope to it. So that would tell us how much current was being drawn. Now, if I just do a single sequence on this, then that's one transmission, and you can see that the current that's being used at different points, there's a big spike at the beginning, and then there's a lower amount when the board's on and transmitting, and that is showing, you can work out from the voltage, and knowing it's a 4.3 ohm resistor, you can work out the current. So I did this spreadsheet, and on here the bit that we're interested in is just here. So I could see that what I did was I made a note of all the different currents. So 190 milliamps, 0.7 milliseconds at the beginning, and then 30, 80, 20, etc. for those durations. And you can then work out the average current, and that's for, if we're doing a 1 minute period, it's going to use 90 microamps. Another thing on this spreadsheet is this is the safe operating voltage and frequency of the clock. So you can see that it's only really safe to use it at, according to the docs, at 3.75 volts. But we've actually run this down to 3.2 volts, even though it should only be good for a 12.8 megahertz clock. So adding the 6 microamps to the 90 microamps gives us just under 100 microamps on average. Based on this, I think a 18650 battery should last 2 to 3 years before needing to be recharged. Right, back to security. So how do we make this communication secure? Well, you could make your own encryption, but this is never a good idea. It'll usually mean security by obscurity and has led to a lot of systems being hacked. Even modifying an existing system should be done with extreme caution. We therefore have 2 main choices: asymmetric encryption, which uses public and private keys, or symmetric encryption, which uses a shared secret. Symmetric is easier and uses less code and memory. For symmetric encryption, you can use block ciphers such as DES, AES, Serpent, Blowfish, XTEA, etc., or stream ciphers such as RC4, Salsa20, and Char-Char-20. Used incorrectly, this can lead to vulnerabilities, for instance, Zoom being partly visible when they used a block cipher, when they should have used a stream cipher. I considered 2 ciphers. AES GCM is a block cipher with 16-byte blocks, and Char-Char-20 Poly 1305 is a stream cipher with 1 bit encrypted for each plain text bit. Char-Char-20 uses an initialization vector to ensure the key stream is never reused. Poly 1305 gives a 128-bit hash to sign the message. For a stream cipher, encryption is bit by bit. Each bit is either inverted or not. So this means that if a bit gets corrupted, only that bit's corrupted, unlike block ciphers where the whole block and potentially subsequent blocks are corrupted. This was my first idea. The IV, which stands for initialization vector, is transmitted unencrypted, and one of the easiest ways to use it is to start at 0 and increment it after every message. It's required to decrypt the message, but it doesn't matter if an eavesdropper knows the IV, so we can send it unencrypted. The payload is encrypted, and the signature is a cryptographically secure hash. But if we are using 32-byte packets, this approach only leaves 4 bytes for the message payload. So a quick comment on the IV. The reason we increment it each time is because we want to prevent a hacker reusing the message. An obvious example is a hacker eavesdropping and then replaying your garage door open command. An easy way to prevent this is to ensure we only accept IVs greater than the previous IV. Back to the message format. We can make the message shorter and we've done 2 compromises. We've reduced the IV to 3 bytes. This limits the number of messages that can be sent. And the other thing we've done is we've sent a partial signature. This is a potential security risk because it's vulnerable to brute force attacks. So the receiver should block communications after a maximum number of messages, and probably that's probably about 16,000 failed messages. The signature might sound similar to cyclic redundancy checks, CRCs, but they can't be used because they're not cryptographically secure. One of the key attributes of cryptographic security is being non-reversible, and CRCs are reversible. In order to implement this, I looked for libraries that I could use, and these are the ones that I decided on. So in order to make sure that this was all working as properly, I decided to do a proof of concept in C#, JavaScript and Python. So this is the C# version, and you can see that I'm using something called NaCl core, which you can get from NuGet, and there's some documentation on it here. So the way that this works is we have a key and an initialization vector and a cipher which we pass the key into, and then there's a encode string method which does the encryption, and the actual line that's important is this line here that actually encrypts it. I decided to base 64 encode it because the data that comes out of this is binary, and I wanted to display this. So then we take the plain text here, we pass this into the encryption method, and then we print out the result. So if I run this, then we can see the result is a base 64 encoded string. There's also a decode method, which is this one here, slightly more complicated because it has to pull the message apart, get all the bits out of it, but then it passes it into the decrypt method, and that's that line of code there. And so what we do is we take the base 64 encoded string, we pass it into this method which will decrypt it and then print the result out. And there you can see the original plain text. The JavaScript code looks fairly similar. This uses the Node.js crypto library. Again, we've got the key, initialization vector, and the cipher. Slightly different syntax, but very similar to the C# code. We have some plain text which we encrypt, and then we print the results out. So if I run this, then we see plain text and the ciphertext. There's also a decrypt method, which again very similar to the C# code. Again, we have to unpack the message, and then we decrypt it with this code here. This prints out ciphertext, prints out the plain text, and again I can run this. And it prints out the results. Obviously, we can cross-check this. We can, which I have. I've cross-checked the C# code and the JavaScript code, and they both produce the same results, and one can decrypt the other. So finally, the Python code. This is slightly simpler because all I've done here is I've created the cipher, I've encrypted some plain text code, and then I've just immediately decrypted it. So again, I can run this, and it shows the encrypted code there, and it also shows it when it's been decrypted. So one thing I want to comment on is the message length. So the encrypted message length is the same as the plain text length. So you may want to pad your messages with blank characters, because it's if there's any possibility that someone could learn something from looking at the message length. So this is the final code. So this is the code that I ended up with, and we'll start with the Arduino code. And what we've got here is the usual setup and loop methods. And in the setup method, I just set up which pins are inputs and outputs, and setting up the temperature sensor. And in the loop method, there's actually I've actually done this as a state machine, but I'll come back to that in a second. And then further down, we've got the method that actually gets the data that we need and returns it as a string. So it gets the light dependent resistor measurement there, then it gets the temperature reading, and then it gets the voltage reading, and then turns that into a string and returns it. The state machine, what happens is in our loop method, we actually come around here, and the first thing that we do, the first state, is we request the temperature, because you actually need to wait about 750 milliseconds for the temperature to be read, and but we don't need to be awake for that, so we power down the Arduino for 500 milliseconds, and then when we come back, we come around and go into state 2, and in state 2 we power up the HD12 board, and then we power down again. That powers down the Arduino, but the HD12 board is powering up. And then finally, state 3, we come in here and we actually read the data and encode it, and then we send it out. HD12 print line, that's actually printing the message out onto the wireless communications. And then we power down. We need to power down in this way, because otherwise things go wrong. And then we go to sleep for 4 seconds. If we have a quick look at the utilities file, we'll see that in there we've got the read VCC method, which we've already looked at briefly, and this uses a trick that the 1.1 voltage reference is actually measured, and it's measured with reference to the VCC, so that actually, if we invert that, we can work out what the power supply voltage is. There's then methods to set up the HD12, and one's to power it down, power it up again, and then there's one to power down the Arduino, and this uses the low power library, and then there's various debug methods. The next one is this encryption one. That's the one that's the important one, and what we've got in here is we've got the key, which is important, and then we've got the initialization vector, which we've put our address in, send address, and we've also started at 1. We have a method here, encrypt plain text, and this actually goes through the process of setting the key up on the cipher and putting the initialization vector in, and then actually doing the encryption there. And then we work out the signature, which we append onto the message, and then we return the whole thing. And we've got another method here, which is increment IV, where that just makes sure that we don't use the same initialization vector twice. So that's all there is to it, really. There's some code after this which is for decryption. I don't actually use that in this particular example, but I left that in there because that may be useful in the future. That's the code for the Arduino. So if we go across to the code for the Raspberry Pi, now I did plan on doing this with Node-RED and JavaScript, but C# is my kind of language of choice, so that's what I've done this in. And but one day, you know, I probably will try to do this as a Node-RED module. So what we've got in here is we've got three files. We've got program, serial and encryption. So the program file this is where we've got our main function, and we parse the command line options. As we saw earlier, we can either decrypt it or print the raw text out, and so that's what this does. And when we come through here, we say create a new serial port, read the data from there, and if we said that we want to decrypt it, then it'll actually do the decryption, and then it prints out the text. The serial file, that's a class which just reads from the serial port. We know that it's going to be on this port here. We know it's going to be 9600 baud, so I've just hard coded all of those in. Really, those should be parameters, or maybe passed in as command line options. And this is a disposable class, so that this port gets closed when we get rid of the object. And what we do is we just read data in and put it into a buffer, and then we say that we've actually read something in when we get a line feed received. So that's all the serial module does. Not particularly proud of this code, but it does the job, and it's not really important for the demonstration. The encryption code is this file here, and there's a big comment at the top of this because this is very much work in progress, and there's lots of things that we could do to it. I've hopefully listed the important things. But the main things here are we've got the key and the initialization vector and ciphers. Now we've got two ciphers here. We've got one for char-char-20 and one for char-char-20 poly 1305, because we're actually going to use that one to check that the signature is correct. Down here we've got a method decode string, and what this does is it first converts the base 64 string into byte array, and then what we do after that is we then parse out the initialization vector and the signature. And then once we've done that, we can go on to this line here, which is actually doing the decryption, and this will always succeed because we're using char-char-20, not char-char-20 poly 1305. So whatever we pass in, it will try and decrypt it, but it'll return the signature as this byte array, which will be an array of 4 bytes, and we later check that. I'll come back to that in a minute. And then what we've got, the other methods we've got here, so we've got poly 1305 match, and this will actually take our short signature, and it'll actually compare that with the one that we calculate from re-encrypting the message. So that should be the same. The bottom 4 bytes should be the same as if we encrypt it using char poly 1305. And then finally in here we've got IV greater than last. This checks to make sure that the initialization vector that we've received is greater than any that we've received before. And that will ensure that we don't allow replay attacks. Now I've put a to do at the bottom here because we should persist the last received IV here, because we should never allow a duplicate IV or the IV to be before the ones that we've received. So if you stop the program and then restart it, it should pick up where it left off before, but it doesn't at the moment. And then and that's the code. And what we do here is to use this is we actually we decrypt the message. So we decrypt the message there, and we print it out, and then we actually check to see if the signature is correct, and if it's not correct then we print out these warning messages. In practice what we would do is we wouldn't accept the message if it failed these checks. You can find all the code on my GitHub repo. Things that I didn't mention that are worth Googling, well I think they are, linear feedback shift registers, LFSRs, can produce extremely long pseudo-random bit streams, but they're not by themselves cryptographically secure, but they are very interesting. And the one-time pad was invented back in 1882 and proved to be secure by Claude Shannon in the 1940s. This is what stream ciphers are based on. So if you look that up, then that'll explain a lot better than I have how stream ciphers work. And finally, A5/1 is a practical example of a stream cipher used for GSM communications. It's been around a while, and it does have people have found some weaknesses in it, but that's worth looking at. So thank you for watching. Does anyone have any questions?
Yeah, key management. So it looked like you had plain text keys there encoded in your binaries, which obviously means you're reliant on physical security and potentially giving you an update headache if anyone ever manages to discover your cipher keys.
Yes, that's true, and that's one of the problems with symmetric encryption, is that you have to have the keys on both ends. And if someone physically steals one of your devices, then you really need to change the keys.
But I guess that asymmetric encryption is much harder to do on a small device as the Arduino.
Absolutely, yes.
Almost impossible. I have another question. Are you sending plain text, encrypted plain text messages? Because I was wondering, why do you base 64 an ASCII text?
The message starts out as text in the first place, and then when you sort of encrypt it, it's turned into binary code. So I just wanted to base 64 encode it so I could print it out, really.
Okay, so you encrypt it before, and then after the encryption you base 64 it before you send it over the wire.
Yeah.
Oh, okay, yeah, that wasn't clear. Thank you.
Something I didn't really make very clear in this, I don't think, was how a stream cipher works. And essentially what it does is, and this is explained in the one-time pad, is that you generate a stream of random bits, and then you XOR that with the plain text message, and then that's what that's what gets sent across. And then the other end XORs it again, and obviously you get the plain text back. So you'll see people that mention that encryption and decryption are the same things, and you kind of think, well, you know, what does that mean? But that's what it means. It's just XORing it bit by bit.
Thank you.
Jonathan, I've used C# to write programs for Windows, but I didn't know you could export to Raspberry Pi. What method do you use?
Yes, it's because it's using .NET Core, and that does work on all sorts of platforms now. It works on Linux. So I did actually write an article about that on Code Project. So if you look at the GitHub page, then I do actually mention where that article is.
Okay, thank you.
And that shows how to. That's based on something that Scott Hanselman did. And I just sort of did a bit of extra work to it, and it lets you effectively cross-compile C# programs.
Great, thank you.
I had a quick question. So you're using fewer bytes. What does it actually mean in terms of practical cryptography? Does it actually make that much difference, or is it just sort of like the side effect of using fewer bytes? Is it actually that much different from a practical point of view? Is anyone actually going to be able to break the code, or is it just
yes.
Bytes?
I mean, if I go back to if I go back to that one there, that's the that's definitely secure, but yeah, you've got a signature that's 16 bytes. So that's the that's quite an overhead. And then the one that I'm suggesting, I cut it down to 4 bytes, which means that if someone someone can brute force attack that, so they could just keep sending you messages until you accept one of their messages. But I think I've worked out that it would take that they would have to send about 16,000 messages before they got one accepted. So it's a bit like PIN codes with your credit card. You want to a four-digit code for a credit card isn't secure. But what they do is they just say, well, if you put it in more than 3 times and it's wrong, then we won't give you your card back. So you want to do a similar thing with this. You want to say, well, if someone sends too many messages through, just block them, just stop it working.
Right. One last question, anyone? No. Yeah. Okay, thanks very much, Jonathan. It's really interesting.
Okay.